two things. One is sky, other one is ocean. Ocean is also blue, and sky is also blue. But why sky is blue? For that, we had the answer from Raleigh, Lord Raleigh's account. Lord Raleigh had done marvelous work on the sound aspect. As an extension of that, the Raman had also studied about his work on the about his work on giving explanation to the flow of the ocean, flow of the sky. What Raleigh had told was when the light enters from this is a very important thing. This is going to be the most important reference for us for the next part of the talk. When the sunlight enters into the atmosphere of Earth, the air molecules they scatter the different rays. You know about the sunlight consists of about all the seven colors. But what Raleigh told was the scattering that takes place while the light travels through the atmosphere of the Earth the scattering is inversely proportional to the wavelength of light. Shorter the wavelength, more will be the scattering. That's the kind of observation we give. So red is going to be scattered lesser, maybe no scattering, whereas blue, violet, and indigo they are going to be scattered most. So what happens is when the beam enters into the Earth's atmosphere, then the blue is going to be, scattering is what scattering is throwing it away. So the light that is coming in the white light coming from the sun, that blue light is going to be scattered all around, and other lights are going to be scattered lesser and lesser. Virtually no scattering takes place from the red and the green. Okay, now what happens is these scattered blue light that is going to come back to us from the scattered direction. The sunlight is going to fall everywhere, but the white light, most of it goes straight here and there. But blue light is going to come back because of the scattering. That's why we see the sky to be blue, because the blue light is scattered most by the atmosphere. What about indigo and violet? Why we don't see sky as indigo or violet? It's because the amount of violet and indigo present in the sunlight is very less. So though it is efficiently scattered, we don't see it because the proportion is very less. So now, you can see here the blue light is being scattered all around, whereas much of the light that is coming, it is spread through the atmosphere. Even this light, the blue light that is getting scattered is not much. It's about say 5%. 95% of the blue light still goes down. Okay, 5% of blue is scattered, and that's what we see as the blue of the sky. So the scattering is so much intensive as the wavelength decreases. You can see the proportionality of Lord Rayleigh derived was it is proportional to inversely proportional to the fourth power of the wavelength. So blue light being present in substantial amount and its wavelength being very less, it is scattered more efficiently. We see the sky. Okay, now one thing. You saw the blue of the sky, they saw the blue of the ocean. And Raleigh tells that sky, he has given the explanation of why the sky is blue. But what about the blue of the ocean? Raleigh told that blue of the sky is nothing special there. It's all reflecting the blue of the sky. Ocean blue is the reflection of blue of the sky. That's what he has told. But Brahman, you see, the Brahma's inquisitiveness was about the richness of blue. The ocean blue is much more intense than the blue of the sky. How can the reflected light be having more richness in the color than the ocean? So you had got that kind of They have got that kind of inquisitiveness in his mind. So he thought he must investigate this. That is the tipping point. But there is the second tipping point. First tipping point was that he saw the board. He didn't know something political future of science. This is the second tipping point that he wanted to see, he wanted to check whether what Aristotle is true. What Aristotle that? What Aristotle was that the blue of the ocean is a reflection of the blue of the sky. He wanted to check that. But how do you check that? You see the way in which he formulates his ideas and the method he devises. He thought that he must check this by means of Brewster's law. You have heard of Brewster's law? Okay. But you know what Brewster's law later? She goes to Oxford, but meanwhile what happens is when he gets down on the land of England, on the shores of England, that Southampton, he gets into the land of Britain. Afterwards, he goes to London and then Oxford. But in Oxford, he buys three things. One is about one direct emission spectroscope, other one is decomposition, other one is one telescope. These three things he buys. Those three are enough to carry out his experiment. He keeps them in his pocket and he doesn't discuss this with anybody there. He meets some great people. So, great people he met. One is J.J. Thomson, W. Trapp. Rutherford became very fond of Raman in the later days. Okay, he completed the thing there. He attended the Congress and he returns. When he returns, this as a matter of curiosity, I would like to tell you. This is England, this is English journal. So there he comes, enters Atlantic Ocean. This is Spain. He goes through a bit of Spain, then Portugal. He comes to the Gibraltar Strait. From there he enters into Mediterranean Ocean. From here to there he travels for nearly 10 days on the surface of the Mediterranean Ocean. During which time it does all this experiment to see whether the ocean's blue is the reflection of blue of the sky. Okay. Now this how many kilometers? 4,000 kilometers. India from Kashmir to Kanyakumari is around 3,200 kilometers. Is even longer than that. Since here is the Suez Canal and here is the Red Sea, then he goes around Somalia and then is the Gulf of Aden and then he enters the Arabian Sea and returns to Bombay and goes back to Calcutta. That is his return journey. But now, coming to the Mediterranean Sea, he travels through about 4,000 kilometers for about 10 days. Then he started doing his work. Get back to this one. You can easily see the ocean's blue is much more than the ocean, the blue of the sky. Thing is, if it is not the reflection of the ocean, the sky is blue, then why the ocean is still blue? That question is there. And we will come to that later on. This is direct visual spectroscope. Means to say, if you see through that spectroscope, you can see the spectrum of the light that is emitted with the source. Nickel prism. This nickel prism, you know what it does is, supposing you see a polarized light, then if you see the same polarized light through the nickel prism and then rotate it, turn this nickel prism around the axis of the light ray coming through, then what happens is at a particular orientation, nickel prism completely cuts off this polarized light. If it is a polarized light, at certain orientation of the nickel prism, the light will be completely cut off. That's one thing that we should remember. Next. Brewster's law is this. See, it's very simple. This is the incident ray, the reflected ray, and this is the refracted ray. This follows the principle of reflection and reflection. Angle of incidence equal to angle of reflection. This follows the Snell's law. Now, one thing you must note here, suppose you keep on changing the inclination of this incident ray, then for certain inclination, what happens is the reflected ray and the refracted ray, they will get right angles. Once the reflected ray and the refracted ray are at right angles, something special takes place. What special takes place? The reflected ray will have all the light rays coming with the vibrations parallel to each other. Okay, I repeat this one. When this reflected ray and refracted ray are at right angles, for a particular angle of incidence it happens, then the reflected ray will have all plane polarized light. What is mean by plane polarized light? It will have the light rays all with the vibrations in all in parallel planes. See, this is one single light wave, it could be any light wave. One single wave means there is no question of polarization. Next. This is unpolarized light. One light wave going this way, another light going this way, and the place of polarization are also changing from with respect to other. This is unpolarized light. If it's a plane polarized light, this is how it looks. Even if it is traveling in different direction, also it's the plane polarized light because the planes are parallel. Okay, next. See now, Brewster's Brewster's law. Brewster's law tells that if the angle of incidence on glass is 53 degrees, then if you look at the reflected light at 33 degrees, the 37 degrees, 53 plus 37 makes it 90 degrees. Okay, 37 degrees to the plane of the glass. If you look at the reflected light from a glass at 37 degrees, then what happens is the light will all be having plane polarized. Now imagine you have a nickel prism and keep on turning, rotating it. It's having plane polarized light coming in now. So at certain orientation, the light will be cut off. Okay, the reflected light will be cut off, all other light will still be there. Now you can see the magic. See here, this is the window pane, and this is the one from which the Nicol prism has cut off all the reflected light. You can see this image is there even here. But the thing is, the reflected light is now overtaken. It's not inside of the window so perfectly. This is only to demonstrate that if you are able to see the reflected light at this angle, the reflected light is cut off. This is the principle what Raman used. This is what I did. Then what, when Raman did this one, you see, going on the deck, he made use of certain cardboard tubes and then went on observing the reflected light from the surface of the ocean around 33 degrees or so. Then he found that by turning the Nicol prism to the reflected light at Brewster's angle, I'm repeating this one. The reflected light is Raman is viewing standing on the deck at the Brewster's angle. Now, holding the Nicol prism and turning it on its axis at the Brewster's angle, what happens is when the plane polarized light enters into the Nicol prism, and while it is rotated, while the Nicol prism is rotated, there is a certain orientation to which the plane polarized light is cut off. It went up, all right, but it did not become dark. It became intensive blue. What does it mean? It means that what you are seeing from the ocean surface, it is not the light that is reflected. If it is reflected light, Raman must have seen dark kind of thing. All light must have vanished from the field of view. But what Raman saw was an intense blue. That means the light that is coming from the ocean is not reflected light. And that light, what he saw after turning off the reflected light was a very rich blue, much more richer blue than what you can see straight without viewing through the reflector. So that gave him the confidence that this is not the way a rally is stored. It is because the light, I told you already, that about 5% of light is getting scattered in the sky and the Earth's atmosphere. More than 90% of the light is getting into the ocean, and that is getting scattered the way. What the air molecules are doing up in the sky, the same thing what water molecules are doing down in the ocean. So the water molecules are again going for scattering this light. When that scattering takes place, even there also blue is getting scattered most efficiently, and you are able to see that rich blue scattered light from the ocean. That's what Raman was able to identify. Then he publishes his paper. He makes the paper hide on the ship itself before he went to the last stop. It is somewhere in Yemen. He posts that particular finding into the Royal Society of London's journal proceedings, and his article on that was published. So that time onwards, Raman's research field changed. He stopped working on the musical instrument, he started working upon the scattering of light. Because that became his prime purpose. What's happening? What's happening when light is getting scattered? Next, the quick mind of Thomas started thinking, well, the light is getting scattered, all right. The light getting scattered from the ocean. It is having blue light on it. But the blue light is the one which was already present in the white light. Now, while the scattering takes place, do I get any issues of other wavelengths? See the way the scientist mind works. First of all, we wanted to see whether it's a scattered light or reflected light. Where it's not a reflected light. Maybe it's scattered light. Scattered light will have the same wavelength as the incident light. Raman's question was, do I get any kind of light that is having wavelength different than the incident light? So that is the starting of Raman will be back. Raman effect is with that aspect of it. Okay, what Raman did later? I will go through the things very quickly. See, Raman wanted to see whether there would be any kind of other wavelengths than the incident light, incident wavelength of the incident light. There was already some interfering phenomena. It was already known during the time of Raman that when you are eliminating certain water body or some liquid body, then there will be some amount of radiations with a different wavelength, not because of the any kind of effect, but only because of fluorescence. You know, I will tell you about the fluorescence. Fluorescence is, see, the light that is falling upon this police person, it is reflected all around. But you see the letters there, POLIC, those letters are actually glowing. That is because of fluorescence. How do you differentiate fluorescence from reflection? Reflection is the light falls and it's going to be reflected or scattered. But in fluorescence, what happens is the incident light is absorbed. The light is absorbed in the material and it is down converted to a slightly lower wavelength and it is re-emitted. But since it is a re-emission but not a reflection, the body starts glowing. We see that as a glow. So what Raman wanted to see was also a change in wavelength, but fluorescence also gives change in wavelength. There is a confusion. See how ingeniously Raman segregated this. That will tell you how. See this is called fluorescence, and every liquid has got certain amount of fluorescence because of the impurities. Okay. Now let's go to the next one. Raman's student, K.R. Ramanathan, he verifies and he says, yes sir, I made the light to fall upon the liquid, and then the scattered light study did have certain amount of change in wavelength, but it's all the fluorescence. No, he got worried. How do I differentiate? Then he told, okay, let's purify that liquid so that there won't be any. They went on purifying, but there is nothing like impurity becoming absolutely zero. But one thing was there. What Raman observed was the intensity of the light that is coming out as a fluorescence, that was not decreasing. So the impurities are decreasing, but the amount of light that is fluorescing is not decreasing. Means what? It means that the light that you are seeing as downgraded wavelength, it is not certainly due to the fluorescence. It must be due to some other effect. So he got some confidence over there. Then they started studying like this. See, you can see here is a monochromatic light. If you have monochromatic light, convert that into a fine bead, and here is a vessel which contains that liquid, and from there, once the light enters into that, much of it comes through. But quite a substantial amount of that light is getting scattered all around. Here the detector, it is going to detect the light from all directions. So how do you get the monochromatic light during the Raman stage? There was no monochromatic light. How much time do you have? 10 minutes, sorry. I will go to this one. Please see this. This is a very important thing. See, he used this is all divided by Raman, there was no standard method. He used a violet filter to the sunlight, not even the visible light, sunlight. Sunlight entered into the laboratory and then it was passed through the violet filter and then it gave the violet light. That violet light entered into this body of the lipid, from there it gets scattered all around. But now you want to see the scattered light and then see the whether there is any change in wavelength, right? So now, how do you see the best way to see the scattered light? Not in the direction of the incident light, but perpendicular to that. So Raman observed to observe the reflected and the scattered light in the direction perpendicular to the direction of the incident light. All right. What happens is this is scattering incident radiation. The violet light is coming like this, but the problem is it may be having the change in wavelengths, but this big brother violet light is going to swamp. It is going to drown the effect of the change in wavelengths with the light of the other wavelengths. So it is going to be a very feeble contribution from the change in wavelength side. Now, how to differentiate that? That is where someone introduced one more thing that is called complementarity. Complementarity, where one is there, the other one is not there. So, what violet does the other complementary color to that one is green. So, where green is going to be observed, violet is not going to be observed, and vice versa. So now he used a green filter. So green filter would absorb all the violet light, but if there is any change in wavelengths, the light of any change in wavelength is there, it will be led through the green filter. So that way divide this method. So now you see the amount of green light that comes out here, that is going to be the change in wavelength. So now you see the whole process. White light, violet light, scattered light. The violet light scattered is now taken off from this filter. Only the light that is coming out from the change in wavelength is coming out. Okay, this is analogous to Compton effect, wherein X-rays fall upon the affect target and it is detected by detector. But the thing is, in the detector you see lambda incident light is equal to lambda dash. That's not an angle. Right. Okay, now January 1928, we are closing down. January 1928, is another student meditation found out that when blue light is incident, the pure is scattered light is observed. That is a wonderful observation. Raman was thrilled to know about this one because that gives his expectation a strong evidence that the scattered light does contain some amount of radiation which are changing the wavelengths from the incident light. Then Rama's most brilliant student was Krishnan. He was doing some theoretical work. Raman engaged him to do this cross-section of the meditation. On 28th February is the day Raman himself observed two blue beam lines for an incident like indigo color. So, two blue beam lines came out with indigo light centered, and in the scattered light we observed two blue beam lines which are on different wavelengths. So that gives the final evidence that there are certainly certain changes in wavelength. Then when the wavelength difference was calculated, then that gave an energy which matched with the vibration energy states of that particular compound, which I do not know what compound it was, maybe it is glycerin, but the vibration energy levels difference between the two energy levels, that energy matched with the energy difference between these two. So that way Raman became convinced. By that time, Compton had also announced this effect. So now it is certainly analog of what Compton had observed for the X-rays. So the same 28th February, he called a press conference and he released that new radiation has been discovered. That's why we consider that scientific. Princess. Next one, please. This is the story behind our science day. This is the actual spectrometer used. Next. Okay, that's what he did by calling the newspapers. Then on 16 March, 16 days later, he came out to the public and addressed a gathering. Where? Bangalore. In Bangalore, where many people do not know, but I know because of what I told Professor Tilumale, that I'll tell you a small. On February 28th, around that, 1978, 50 years Board Jubilee celebration was conducted in the Center College, Center College Physics Department. I was doing research at that time. All the people, prominent people who were associated with Raman effect, they all assembled there. They celebrated this Raman effect, Board Jubilee for 3 days, which I had witnessed myself. I was able to see Lady Raman. Raman, unfortunately, I have not seen Raman in my life. 1970 passed away, but 1978 this was conducted. Lady Raman had come. Raman's most important footage has come. Raman's reviews. I met all those, and in fact, I've seen other things like Raman's gold medal also. I've seen in Raman students, but not Raman. Now that chamber, that where the Raman medal announcement, this particular hall, it is there still in the London University Center College, P2 hall. Is now named as the Raman Hall. Okay, I was sitting there in third row when Raman's another nephew by name is Chandrasekhar, famous for his liquid crystal research. He stood up and told, "Let this hall be named as Raman Hall." So that was named as Raman Hall afterwards. This. That is the hall. Next one. Okay. Next one. Next. He was part of the Nobel Prize for the discovery of love because that was the first physical effect that gave us the idea of a provision to probe into the far infrared region of the universe. So Raman effect became very important for the physics research because we were able to probe into the far infrared region of the spectrum. So now, let me not worry about why it was selected for the right. And he was, we can see here, Raman sitting in the hall. We can see where he is. See here, the turban, that is Raman. Next one. Next one. Again, this is Raman. Same photo, another angle. This is the banquet hall. After the Nobel Prize awarding ceremony is over, they after lunch. In that lunch, you can see here all these royal family members and courtiers, and all the invitees along with the award winners were seated here. Can you identify where is Raman? Nobody can identify, but yes, it is not here. It is like. I tell you, see, Professor Ramasishan told, when I was attending his talk, he told Raman was sitting here. See the Raman? Raman had told Ramasishan that it was he. He was sitting there. So that is authenticated, his position is authenticated. Okay, next. Next. This is with the other Nobel laureates. Next one, another photo of the other Nobel laureate. Next one. Voice. Next one. Next one. Okay. This is common sight to visit before got the Nobel Prize. Sommerfeld visited Calcutta in the Dye Association Laboratory and then he appreciated Thomas work. And in fact, he was one of the people who recommended Thomas name for the award of Nobel Prize. After he got the Nobel Prize, Rutherford recommended Thomas to become the director of the Institute of Science, where all the previous directors were all Britishers. Raman was the first Indian director. Next one, please. That is Millikan. Millikan, Lady Raman, Raman. Next. All three hungry. Okay. The last thing. I will catch up with executive. See, Raman became the director of Indian Institute of Science, all right, but afterwards something happened. The Britishers, the managing committee, they did not like Raman to be there. All of you, please. I'm waiting up it. See, what happened was the other directors, the managing committee was mostly governed by the Britishers. They wanted to put down Raman. They found out so many things which were not according to them. Raman took several kind of things for granted because it was all done in a fairness. But they did not take it that way. They asked Raman to resign. Raman was supposed to resign, but at that point of time, one Diwan of Mysore named Sir Mirza Ismail. He came in support of Raman and he told, okay, let him be taken out director, but let him stay as the professor of physics. So Raman stayed as professor of physics until his retirement as a professor of physics. Then he came out and established a new institute by the Raman Institute, which I do not have time to explain to you now. With this one, I would like to complete my talk. There is a very questions you can please ask.
Any questions? I know what is your question. Okay, yeah, we are at the end of the session. Really, it was wonderful, sir. You have given glimpses of life history of C.V. Raman. Of course, many of the things even we don't know. But thank you very much for giving us such information, which are very, very, even without very information for us. So, thank you very much for doing so.
PPTs ತಗೊಂಡಿದ್ದೀರಲ್ಲ PPTs ತಗೊಂಡಿದ್ದೀರಲ್ಲ ಕಾಪಿ ಮಾಡ್ಕೊಳ್ಳೋಕ್ಕೆ ಕೊಡ್ತದೆ ಸರ್ ಶೇರಿಂಗ್ ಓಕೆ ಸರ್ ಓಕೆ ಸರ್
Thank you, sir, for enlightening us the knowledge about Sir C.V. Raman. Starting from his early life to his research and the discovery of Raman effect, it was really wonderful. Now I request all the dignitaries to felicitate Dr. Basuras.